All right, in this lesson, we are talking about quadratic transformations. And so we are starting with the quadratic parent function, which is f of x equals x squared. And so to get some points that we can graph, we are just squaring our x values. So negative 3 squared would be positive 9. Negative 2 squared would be positive 4. Negative 1 squared would be positive 1. When you square a number, you're multiplying it by itself. And so negative times negative will always give you a positive. 0 squared is obviously 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. Okay, and so we have 0, 0, 1, 1, 2, 4, 3, 9. And then the negative x values give us the same outputs because when you square a negative, it becomes positive. And so it creates this U shape called a parabola. And so a lot of the key features are similar to absolute value, only it's not linear like a V, it makes a U shape. And so we still have an axis of symmetry down the middle at x equals 0, and so it's important that you write the x equals in front so that you're talking about a vertical line. And so axis of symmetry is x equals 0. And then we still have a vertex, which is this minimum. It's an absolute minimum. At 0, 0. And so whenever you talk about the minimum value, you're talking about the y value. And so this 0 is the minimum. And so because that 0 is our minimum, that means our range is going from 0 to infinity, including the 0. So use a bracket. And then just like absolute value, domain is all real numbers all the time. It's going forever to the left, forever to the right, no matter what. Okay, and so those are some key features, and just like with absolute value, we're also going to be transforming it. And so remember when you had a plus 5 outside the function or outside the bars, that moved you up 5. And so for a quadratic, it's going to be outside the square, whereas a minus 5 is going to move you down 5. If you are inside the square, you have to add parentheses. And so inside the square would move you left and right. And anytime you're inside the parentheses, it's opposite of what it looks like. I call the parentheses the crazy house. Everything's backwards and crazy. So minus moves you right. Plus moves you left. A negative outside the square will not have parentheses, whereas a negative inside the square must have parentheses. So it's very subtle. Okay, so technically there are invisible parentheses only around the x. And so this negative is outside. It would look like outside the bars. This is your reflection over the x-axis. And so it's your vertical reflection. A negative inside is your reflection over the y-axis. So you're not going to see a change. Okay, the y-axis is the axis of symmetry. And so it looks the same, whereas a reflection over the x will actually cause it to be upside down. If you have a scale factor outside the square, there's no parentheses. If you want it inside the square, you must include parentheses. Outside would be your vertical stretch by 5 if the number is greater than 1. It would be a vertical compression if the number is smaller than 1. Okay, so I'm going to write it out. Vertical stretch, just in case you're not used to those abbreviations, and vertical compression. Okay, and so if you think of a rubber band, if I'm holding a rubber band and I stretch it vertically, it's going to be narrower. Okay, and so the bigger that number is, the narrower your graph is going to look because the more it's being stretched vertically. The opposite is when you compress it. If you make it smaller or shorter, it's going to look wider. Okay, and when your scale factor moves inside the parentheses, it's the opposite of what it looks like, and it's horizontal. So this is actually your horizontal compression by 1/5. And it would also result in a narrower graph. Okay, and so whether the 5 is inside or outside, it's gonna cause the graph to be narrower. In the case that it's outside, we called it a vertical stretch. In the case that it's inside, we called it a horizontal compression. Horizontal compression. That's going to cause it to compress horizontally. So if I compress a rubber band horizontally, I'm making it narrower. Okay, and then our horizontal stretch by 5 would have a 1/5 inside. Everything inside the crazy house is backwards. So there's our horizontal stretch by 5. Okay, and so this would be wider. Think of stretching a rubber band horizontally, it would be wider. Okay, and so this equation is something called vertex form. And we'll talk about that more next lesson. But it's called vertex form because you get the vertex for free just by looking at the equation. You can see that it's been moved right H and up K. And so that would put your vertex, hold on, right H up K. Right H up K. So that would put our vertex at H comma K, which means our axis of symmetry would be x equals h. It's whatever the x coordinate is. And then you have an x equals in front of it. Okay, the domain of a quadratic function is all real numbers all the time. And then the range depends on whether a is positive or negative. If a is greater than 0, it opens up. If a is less than 0, meaning there's an Rx, a reflection over the x-axis, it's upside down. It also tells you how wide or narrow the graph is, okay? And so larger A means narrower. Okay, and so if there is no Rx, meaning A is positive, our range is going to go from K to infinity with a bracket. Okay, because here's our graph at HK with the vertex. And so it's always above the K. Whereas if A is negative, it's going to be opening down. And so K would suddenly be our maximum value. Okay, K here is a minimum. In this situation, K would become our maximum. Okay, and so we're going to do some examples of just identifying the transformations, and then we will graph some. Okay, so for this function, there are 4 transformations. The first one is this negative out front. That's going to be our reflection across the x-axis. So we know it's opening down. Next, we have a 1/3 in front. That is going to be our vertical stretch by 1/3. And you can just write VS 1/3. Okay, and so we know it's going to be wider because it's shorter. Think of vertically compressing a rubber band. So if you want to just put wider in parentheses, you don't even have to write that. I just want you kind of visualizing what the graph would look like. And then we have this -7 inside, so that moves us right 7. And then we have a +6 outside, that's going to move us up 6. Okay, and so right 7 up 6 puts our vertex at 7, 6. And so you can picture it opening down because of the reflection, vertex at 7, 6. Okay, and so that means the axis of symmetry, which has an x equals in front of it, 7, the x coordinate. Our domain will be all real numbers all the time, so you could go ahead and fill that in for every single one. For the vertex, it's an ordered pair. For the axis of symmetry, it's an x equals equation. Okay, and then our range, because this 6 is a maximum, our range is going from negative infinity to that 6. And we actually equal that 6, so use a bracket. Okay, this next one isn't in the correct form, and so on your test, it'll be written in the correct form. I'm gonna go ahead and write it in the correct form for you. If you have a scale factor and a plus number inside, you need to make sure you have double parentheses. So since they didn't do that, I'm gonna fix it for them. And this is how it would be written on your test. Okay, and so my first transformation, reading from left to right, is this 2 inside. So we're inside the crazy house now. Here's the crazy house here. Okay, and so it's backwards. You'd want to say horizontal stretch by 2, but it's your horizontal compression by 1/2. Okay, so you know it's going to be narrower. Okay, next we have a plus 1/2. That's going to move us left 1/2. And then we have a -7 outside. That's going to move us down 7. Okay, and so we haven't reflected, so it's still opening up. And left 1/2, down 7 would put our vertex at -1/2, -7. -1/2, -7, which means my axis of symmetry is x equals -1/2. Don't forget the x equals. And then because the -7 is a minimum now, my range is going from 7 to infinity, to positive infinity. Okay, if it's going to negative infinity, make sure you put the negative infinity first. Always least to greatest, bottom to top. Okay, last one like this. Be careful, there's no parentheses, so this negative is outside. If there's no parentheses, it's outside. So that's going to be your reflection across the x-axis, which means it's opening down. The only other transformation I have is this down 4. And so that means the x-coordinate of my vertex is still 0. We didn't move left or right, but we did move down 4. Okay, and so 0, -4. And so x equals 0 is our axis of symmetry. This -4 is a maximum now. And so my range is going from negative infinity to 4 with a bracket. Okay, example 4 says, write the equation for g of x if g of x is formed by reflecting our parent function, x squared, across the x-axis. So we have x squared reflected across the x-axis. We have a horizontal compression by 1/2. Rewrite that as a fraction. And then shifting left 3 and up 11. Okay, and so when we write our equation, We need parentheses squared. The parent function is squared. That's not a transformation. That's just what the parent function we're dealing with. So don't forget your square. You'll lose points for that. Okay, and so we're reflecting across the x-axis. We need the negative outside. Horizontal compression by 1/2 would put a 2 inside the square. Left 3, that means we're going to also need a double set of parentheses. Left 3 would be a +3 inside, and then up 11 would be a +11 outside. So left 3, up 11. Double parentheses, super important. Okay, so now we're going to graph these. Okay, so starting simple, we have x + 5 squared + 3. 2 transformations, left 5, up 3. Okay, and so just to put our parent function on the grid, remember it's 0, 0, 1, 1, 2, 4, -2, 4. Okay, so to notice the pattern of these points, your first points on each side of the vertex, your vertex starts at 0, 0, and then you go up 1 over 1, up 1 over 1 on each side. And then your next good point is over 1, up 3. Okay, and so the x's are always going by 1, but the pattern in the y's are up 1, then up 3. Okay, and so that pattern should still hold true if there's no stretch or compression. Your change in y's are 1, then 3. Okay, and so left 5, up 3 means the vertex is now at -5, +3. So -5, +3, there's the new vertex. But the pattern of the point should still be the same. I should have 1 on each side, up 1 over 1. And then if you want the third point, go over 1, up 3. Over 1, up 3. Okay. And so there's the red function. Okay, for this next one, we can see that the vertex is right 3, down 4, but we also have a reflection. Okay, and so this one's going to be upside down at 3, -4. So 3, -4, and then we still have the 1 point on each side, and then the next point would be 3 away. Only now we're upside down. But the pattern of the points has not changed because there's no stretch or compression. Okay, next up, we have h of x. So this was f of x. Green was g of x. Now let's get h of x. He's been vertically stretched by 3, right 2, up 1. So his vertex is 2, 1. Still opening up, but he's going to be narrower. Okay, and so instead of our y's going 1, then 3, that's going to be changed by a factor of 3. So 3, 9. Okay, and so let's get the vertex first. 2, 1. Instead of going up 1 over 1, we're going to go up 3 over 1. Up 3 over 1. Okay, and then that's going to be enough to graph your point. The next point would be 9 more units up, which would fall off our graph. So over 1, up 3 because of the vertical stretch by 3. The rest weren't, so you still have the up 1, up 1. You can kind of treat it like slope for those first 3 points in the middle. All right, this next one's in really bad form. First of all, this 0.5 is a 1/2. And when we give it to you on the test, it will be in proper form. So I'm going to go ahead and rewrite it for you. Factoring out the 1/2, you won't be expected to do that yourself. And so we've got a lot of transformations. Let's do this one in blue. Okay, And so here's our function, and that's how it will be given. We have an Rx. We have a horizontal stretch by 2. We have a left 6, down 1. Okay, so vertex is -6, -1, and it's opening down, and it's going to be wider because of that horizontal stretch. And so my x's are going to change by 2's. Okay, so let's get the vertex, -6, -1, and then to get our other points, instead of going down 1 over 1, this is if there was no stretch or compression. Those would be my points. But because we horizontally stretched by 2, you're going to take these points and make them 2 away in the x direction. Okay, so it's kind of like your slope is changing to 1/2 here. Okay, so down 1 over 2, down 1 over 2 to get your 2 points on each side. Okay, and then to get your 3 away point, it's going to be 2 more units. You just stretch all your x distances by 2. And so that's how you do your horizontal stretch.